I'm Kelly, and I'll be speaking to you today about my PhD project, which is all about the simulation of reflectance for characterization of particle suspensions. As we all know, when you have turbid media, like is shown in the picture here, which is this one? As shown in the picture here, you start to get a bit of a clouding of your signal. And it's unclear, as the turbidity increases, whether this peaks absorption, scattering. We don't really know. There's nothing you can really do there to enhance that. So what's the way around this? Well, one way is to use DRS, or diffuse reflectance measurements. So my colleagues in the lab, we have this little probe here, which just sends out a white light signal from 3 possible sources. So we could have one from normal incidence, one from 45 degrees, and one from 30 degrees, which is actually shown in this bottom picture here. We insert it into the sample, whatever your sample is, switch it on, and then all these little fibers here, they just are receiving fibers which collect back the scattering information. Great, but how on earth do you figure out your absorption or your chemical composition and your particle size from this? Well, we now have to go on and consider some theory. So we move to me theory, and this is just a typical diagram of a typical particle suspension. We have a percentage, which is a volume fraction of the medium, which in our case is water, and we have a percentage of the medium, which is volume fraction of the particles, which in our case is polystyrene. So we want to know the absorption coefficients and scattering coefficients for this sample. First of all, we've got to consider the bulk absorption coefficient of the medium, the water, and then we move on and we consider, okay, so that's great, so we now need to consider the absorption coefficient of the particles. So what we do is we take an absorption cross-section of this, which we can calculate through me theory, which essentially just uses Maxwell's equations, which I've not shown here, and we can get this for our particles, which is multiplied by the volume fraction of the particles which are in our system. To get the total absorption coefficient, we just add these two things together, and it's done. I did mention scattering earlier. So how do we manage to characterize this? Well, we imagine a particle, and we have incoming photons here. The scattered light will array itself out like so. We can take a cross-section, again, which we can calculate through me theory once more. And if we calculate this again by the volume fraction of the particles, we will have our μs, our scattering coefficient. However, it's not the end of the story. So we now need to consider the phase. So what directionality is going to happen from the scattering? So in order to do that, we have to then consider this anisotropy factor here, or this G factor, and we can combine it into this μs prime, or reduced scattering coefficient, as shown here. This is good, but this is just for single photon scattering. We need to scale it up. We need to now consider multiple scattering. So we have to move to the radiative transfer equation. So we're going to start to build it up bit by bit. This term here just represents the convection flow of your photons through your sample. The radiance here is kind of like a counter. So it's kind of like a guy with like a counter at door. However many people are going through that door, it will click. So however many photons are going to go through a point R in space in the same direction, S, it will count. We then move on and consider just the losses due to absorption and the losses due to scattering away from this initial convection flow direction. And we also have to then consider scattering back into the initial direction. And finally, we consider the source, where the initial thing's coming from in the first place. My supervisor gave me an excellent analogy for this equation. Consider your source as like a train. So there's a bunch of people getting off that train, and they're going to move in a convection flow outside the station. There are going to be people who just stop to tie their shoelaces. They can be considered like absorbed. They're gone. There's people who will bounce off to the toilets. They're scattered. They're gone. But there's also, the same people could then come back from the toilets and go back into the initial flow direction, which is kind of like what we have here with the phase. Now, this equation in its current form is unsolvable. It would take a lot of computation time, and the reason for this is because we are considering every possible scattering direction within a solid sphere. That's huge, that's a lot. So we have to make an approximation, and in my case, I use a diffuse approximation. But before I get to this, I should mention that there's a little bit of a trickiness with this equation, or this diffuse approximation. And that is because if you're close to your boundary, the order of spherical harmonic, which we use to basically represent this scattering phase function thing, it increases exponentially, and it decreases exponentially with distance. So really, you've got to be at this point here inside your medium before you can actually consider you've got isotropic scattering or close to isotropic scattering for a diffuse approximation to work. So that's the little tricky bit for the experimentalists, not for me, but for them. So moving on to the diffuse approximation. As I said, we kind of cut off at the first anisotropic term. So for the first anisotropic term in spherical harmonics. After a bit of maths, basically, we can arrive at the diffuse approximation as shown here. And this is just showing you again, this is the mu(s) prime. So this is good. How do you solve this? Well, luckily for me, some guys back in the 70s did solve it for a very similar system to what I have, in which they considered that you have diffuse reflectance at 2 different radii, and you take them away, and that means you get the diffuse reflectance within this toroid from your source here, and you scale it to your receiving fiber, which is exactly what our experimentalists have in our lab. As I said before, with this diffuse approximation, it's good in the bulk of the system, really poor near the boundary, and for reasons I've just mentioned, like with the spherical harmonics, it can't really accurately determine these boundary conditions. Okay, so what do the experimentalists give me? Well, I get something like this out from them, which is the reflectance gathered at these 3 probes here with this source turned on. You can see they all follow the same trend, which you would expect because it's equidistant and the light source is coming in at a normal instance. They did it for 45 different polydispersed polystyrene suspensions. I should mention here that I'm only considering the monodispersed model. A colleague of mine, Daria, who's co-author of this paper, she is considering polydispersity. So if you've got any questions about polydispersity, don't hesitate to email, she'll love it. So they did it for a radius range of about 72 to 279 nanometers and a concentration of about 2% to 15% weight. And I should mention here as well that there's a scale factor due to the calibration of the instruments, but this really should be independent of the sample conditions. Now moving on to the bit that I do. So this is just a schematic which shows the optimizer which I made. I received the data from these fibers. I put an initial guess of the radius, the concentration, and the scale, which can be turned on or off whether it will vary or not. It then runs it through me theory, calculates the reflectance, fits using differential evolution method, which is essentially just trying to find a global minimum for your system. So it's trying to find the place where it's got the best sort of global minimum. It then asks itself if it's okay. If not, it'll readjust the parameters which I've switched on, run it through me theory, and then pass the readjusted parameters back into the reflectance calculation, and round it will go until it eventually says to me, okay, I'm as good as I'm going to get based on the model you have given me. So what do I get out in the end? Well, this is for a particular sample. These green lines here are just lines that I fed in using the exact experimental parameters and just scaled them up so that they were in the same range as the other data. So you can kind of see already that polydispersity might be having an effect here because this shape should be matching what the fibers are giving me, but it's not. So already you can kind of see maybe polydispersity is playing a part. But these dark blue lines are my fits. I did one where I varied the scale and one where I fixed it to the average scale that I found. We can see when I varied the scale, the trend overall for the full spectrum is much better. And when I fixed it, I kind of lost this bit here, and this bit here is not so great either. But this middle bit is okay. And when we look at the numbers, we can kind of see an interesting trend in that when I vary the scale, the volume fraction I found for the particles is off by quite a bit, but when I fixed it, it's almost exact. However, when I vary the scale, I get a much better representation of the radius than I do when I fix it. So I was interested to see if this trend continues across the 45 samples. So what is shown here is the data from the 45 samples with the squares being fixed scale and the triangles being varied scale. If everything matched exactly, they would lie upon these two black lines. Doesn't match exactly, as we can see, but the trend actually still happens. So when I vary the scale, the radius is captured much better, but I lose the volume fraction entirely. And when I fix the scale, I catch the volume fraction much better, but I lose the radius. And this can be seen again in these difference plots with chi-squared. So it thinks that this volume fraction for a varied scale is great, but we can see that it's not. And when I fix the scale, we can see that the cluster here is much better, and the opposite is true here. So moving on to some conclusions. I developed the optimizer using physical theory. It's a one-step process. And I have a little bit of a Heisenberg principle thing going on. So when I fix the scale, I get the volume fraction but lose the radius. When I vary the scale, I gain the radius but I lose the volume fraction. So some future work. I will be going on to continue to explore this, and I'm hoping that by fitting at a different distance as well as the one that I'm fitting at just now simultaneously could fix this. I also want to utilize the full functionality of the equipment we've got in the lab and fit for an angular light source. And finally, I want to try to fix this boundary layer problem that I've talked about before with the spherical harmonics, basically trying to include some of these higher order terms to better count for this boundary layer. I would just like to thank all of my colleagues and the University of Strathclyde for funding my project. I will now take any questions.